Do you think we've left it long enough?
Okay, so thank you everyone for coming. Today we have Ultracold, who is at the University of Oxford, and DEVANG NAIK, who is at GPPM, remote CNRS de recherche, I imagine. Yes. Richard is a theorist. He has some papers. He started a line of research with Feshbok and on doing tests of quantum gravity using Bose-Einstein condensates. And DEVANG is an experimentalist with a lot of expertise in all things quantum gases. And this is a paper that I had a minor contribution as well about testing quantum gravity with a non-Gaussian and Bose-Einstein condensate.
Okay, all right. Hi, everyone. So yeah, let me take this opportunity to say thank you to Marius and also Czaslaw for having both me and DEVANG here. Yeah, it's already been a lot of fun, and looking forward to some more exciting discussions over the next few days. Yes, as Marius said, this is a paper that, well, this talk is about a paper that was about testing quantum gravity in the lab that was published last year with myself, DEVANG, and Marius. It wasn't such a minor contribution, and some others. And yeah, I'll provide the, so it's a bit unusual today, it'll be two people talking, so I'll provide the motivation and the more theoretical aspects of the work, and then I'll pass you on to DEVANG, who will provide experimental expertise on what is needed to make this sort of test a reality. Okay, so I actually have a particle physics background, which normally I don't like to admit, but when we used to discuss... No, I know, yeah. Yeah, but so we used to discuss how to see quantum gravity effects in experiments back then, and but we always used to speak about how you have to go to the Planck length scale, which is unimaginably small. It's 10 to the minus 35 meters. So this is where the Schwarzschild radius of a black hole, so its event horizon, is comparable to its reduced Compton wavelength. So a place where GR truly reaches the microscopic world of quantum theory. So, and all sorts of things are predicted to happen here, such as vacuum fluctuations of space-time curvature completely distorting your measurements of distances. Or perhaps less interesting, it could be the length of strings in string theory, for example. So the idea is to probe this scale, you would have to use a particle accelerator, as these are essentially the best microscopes that you can build. But in this case, to do that, you'd have to smash together subatomic particles with Planck energies, which seems way out of reach. People talk about using accelerators the size of the solar system to get enough energy, or even the Milky Way. Okay, so it's not going to happen. If it could be done, though, then theoretically, in principle, this would be a way of distinguishing between different theories of quantum gravity. But that presupposes that gravity must be quantized, which is what the vast majority believe, and I think for very good reasons. But there is no actual experimental evidence for this, so we cannot say for certain right now if there is a quantum theory of gravity. Indeed, in the early days of trying to unify GR and quantum theory, there was a bit of debate about whether gravity should actually be left fundamentally classical, since it's much harder to quantize than the interactions, and it's also theoretically quite distinct. So, for example, it has background independence, and none of the other interactions seems to have that. So maybe a different approach should be taken with gravity. So that led to a few theories over the years where we keep gravity fundamentally classical, but we still quantize matter. So an example is semi-classical gravity, where the fundamentally classical gravitational field is sourced by the expectation value of the energy of quantum matter. Okay, so these are fundamental set of equations. They update the Einstein equations. So this is space-time curvature, essentially, and this is the energy of matter. And yeah, you should read these as fundamental equations. They're kind of God-given. Okay. And there is also some debate that these theories will always be played with theoretical issues such as superluminal signaling at certain scales. But until we're able to rule them out, we have to keep them. We have to say if they. We can't say if they definitely should be ruled out or not until we have experimental evidence to do so. And on the flip side, if we did have experimental evidence to rule them out, then this would provide experimental evidence for quantum gravity or a quantum theory of gravity, which I think is very exciting. So some of you probably already know that this subject was much discussed back in the 1950s at a Chapel Hill conference, where Feynman introduced an idea for how you could test if gravity is fundamentally quantum or classical in the lab. So it was a thought experiment, and from the proceedings of this conference, I don't think it's 100% clear what exactly the experiment was, which perhaps has led to some confusion. But at least my take on it, so you'll just have to take this for granted, is that there is a Stern-Gerlach device which is used to place a macroscopic mass in a superposition of two locations. So that's the circles on the left. And then there's another mass which is not initially in a superposition, so that's the mass on the right, which is near this left mass. So then if gravity is quantized and quantum theory is universal, this mass in a superposition of two locations should put the gravitational field or force in a superposition. And this will then cause the mass on the right to go in a superposition branch of going one way or the other. Okay, so although Feynman never explicitly states it, the systems will become entangled. Although he does talk about using some reverse Stern-Gerlach devices for measurements, so maybe he did have this in mind. Okay, so quantum gravity leads to entanglement, but if we have a classical theory of gravity, then we cannot have a superposition of gravitational fields or forces, and so this white mass will not become part of an entangled state. So in this sense, this thought experiment provides a way of telling if gravity is fundamentally quantum or classical. Yeah, so before we spoke about how you'd have to go to the Planck length scale to see quantum gravity effects, but this sort of test seems to be better characterized by the Planck mass scale, which seems far more within reach. It's about, well, for composite mass at least, it's about the mass of a flea egg. And yeah, this was actually nicely demonstrated by Marius in the context of more recent proposals, and also connected to some old ideas of Penrose that this is another scale where the unification of gravity and quantum theory becomes important. So in trying to understand what's going on here, I like to think that with this particle accelerator experiment, we're in some sense bringing gravity, bringing space-time curvature to the traditional microscopic scales of quantum theory. Whereas here, we're sort of doing the opposite. We're going into a different regime. We're bringing quantum theory, bringing quantum coherence to the traditional scales of gravity with large masses. So, yeah, until relatively recently, this proposal of Feynman's had somewhat been forgotten about, perhaps because technology was going in the direction of particle accelerators and probing smaller and smaller length scales. But as progress in that direction seems to have slowed down, rapid developments have been made in taking quantum theory to larger scales, and that, of course, has then resulted in this proposal coming back to interest. And particularly, there's been a lot of interest in this idea that entanglement could be used to verify the quantum nature of gravity. And this has resulted in a fairly general argument that if you have two matter systems, let's call them A and B, and they only interact with the gravitational field, let's call it C, so they can't directly interact with themselves, then if we have a classical theory of gravity, by definition, we cannot entangle this with a quantum matter, a quantum mass. And so therefore, there is no way that these two masses could become entangled in this way. Whereas if you have a quantum theory of gravity, then you can entangle gravity with a quantum mass, and so in principle now you can entangle the two masses in this way. Okay, so the idea then is that if gravity acts locally, seeing entanglement would be evidence of a quantum theory of gravity. Then using this argument, two papers appeared a few years ago, which demonstrated that a real test of quantum gravity may really not be that far away, relatively speaking. Okay, so these papers, they boost the proposal of Fein's proposal by now putting this probe mass, the mass that was on the right, in a superposition of two locations. So we now have two masses that start off in a superposition. And rather than looking at the entanglement due to how this white mass moves, now we look at the entanglement due to how gravity creates a relative phase shift in these superposition paths. So can everyone see the slides despite the boards? Yeah, just a bit of it. Yeah, okay. Okay. Yeah, so if you take the Newtonian regime of gravity, and let's say we say that these masses are close together, then this phase shift that is responsible for the entanglement can be written in this way here, where the mass is in the Planck units. This is the time of the experiment and the distance between the microspheres. And then maximum entanglement is when this phase difference is of order 1. And this could, of course, be achieved with various experimental parameters. And these are the ones that the original Bose paper assumed. And yeah, I'll talk about the feasibility a little bit on the next slide. So these papers made a big impact, which of course will always lead to a lot of discussion and many questions. And I'm not going to go through all the questions that have been raised in the literature, of course, but I'm going to talk about just one or two because that's going to provide the motivation for the rest of the talk. So one of these questions is to do with locality. So locality can mean different things, it seems, in different communities. And here by locality, we mean that these two masses must not directly interact with each other. Now, of course, locality is, so yeah, that means that obviously the gravitational interaction must be local to each mass. Yeah, so I mean, locality is it's an important tenet of modern physics, and we have evidence that this is the way nature behaves. So perhaps, you know, it would be rather peculiar if the way GR and quantum theory meet is non-locally, especially at the scales of interest. So, you know, this locality assumption seems fairly reasonable. What has all this discussion been about? Well, I think there are a few discussion points. So one of these, perhaps in order of importance, is that, although it's not quite the same perhaps, non-locality often crops up when you try and unify gravity and quantum theory in quantum gravity theories, such as string theory, which actually can be approximated by a non-local quantum field theory at lower energies. And it's also been suggested, non-locality has also been suggested in classical theories of gravity as a way to explain dark matter and dark energy effects, okay, as a way of not having to introduce actually dark matter and dark energy. And perhaps more importantly, there are even some discussions that if you want gravity to be fundamentally classical, then you're going to be led to a non-local theory in general because of how classical gravity is sourced by quantum matter, which is obviously something that's rather peculiar. You don't have that in a normal quantum theory. So even some suggestions that semi-classical gravity, the sort of archetypal theory of classical gravity, could be non-local due to its non-unitary dynamics and non-linearity because of how classical gravity is sourced by the quantum expectation value of quantum matter. And so there's ideas that if this theory is treated absolutely rigorously, then it could actually create entanglement in the experiment. But you know, I don't think that's been achieved yet. That's just, these are, I think, mostly ideas at the moment. But I don't want to go into the details. I really just want to highlight that there has been a lot of discussion on the generality of this entanglement argument given this locality assumption. And also that it might, well, it seems to have led to a few confusions. So, for example, as I said in the previous slides, in those entanglement papers, they use Newtonian gravity to describe the entanglement effect. And, of course, Newtonian gravity is non-local. So you could be led into thinking that, well, gravity is always going to create entanglement in this experiment, irrespective of whether gravity is classical or quantum, because gravity is non-local in this regime. But, of course, at least in my opinion, that's not true. We have much evidence to believe that gravity is relativistic, and it always behaves relativistically, no matter what scale you're at. And Newtonian gravity is just used an approximation, of course, in these papers, nothing more than that. And so we rigorously go through this in a recent paper, where we describe these experiments from the point of view of relativistic quantum gravity now. And we show that entanglement only occurs between the masses after the light crossing time between the masses. Now, of course, there are questions also on the feasibility. So, for example, we'd need superposition states to increase in mass by around 9 orders of magnitude compared to what we can do in the lab at the moment. And still for these to have long coherence times and large separations. So coherence times of around seconds and separations around micrometers. So there is no getting away from this would be a big jump experimentally. But the field does seem to be making rapid progress, so there's also hope that we will get there. But I would say that at the moment it's rather unclear how far away these experiments actually are. If we're talking 10 years, 20 years, 30 years, 40 years, 50 years, okay? And also some other questions that are not so related to the talk, but I can talk about afterwards. Okay, so you can probably tell I'm not especially worried by some of these questions, but we still decided to explore whether there was rather than just using these entanglement experiments, if there was an alternative approach to testing quantum gravity that could help answer some of these questions. So entanglement has been looked at a lot. Well, this entanglement argument has been looked at a lot, and not just from a quantum theory perspective, but also now from a more theory-independent approach, using generalized probability theory and constructor theory, for example. So not relying then on the specific dynamical laws. Whereas as a first approach to looking for an alternative approach, we're just going to follow a dynamical law approach and ignore theory independence, and hopefully we'll tackle that another time. Okay, so saying that, what I'm going to introduce this alternative approach with is weak field gravity. So this is where you split the metric into a background and a perturbation, and then gravity and matter interact through this interaction Hamiltonian density term, where you have the stress energy tensor of matter and the perturbed metric. And then if, just as with the entanglement arguments, we assume that all of interactions can be neglected, and we take matter to obey field theory, then this stress energy tensor will necessarily be quadratic in the fields because it just contains the kinetic and mass terms. And here, I've just taken a real scalar field to represent matter, but this is just for simplicity. This would hold for all types of fields, spin half, spin 1, etc. So then we also assume that in the experimental regimes of interest, a matter obeys quantum field theory. So now we add a hat to phi, and here's our new stress energy tensor. Then if we have a quantum theory of gravity, it seems reasonable that there should be some quantum operator then associated with some of the components of the perturbed metric. So we add a hat to this as well, and this is then just standard linear quantum gravity. Whereas if you have a classical theory of gravity, then there should be no quantum operator associated with the metric field, so we leave this hats, okay? But we still, of course, quantize matter in that case. So these are the two different theories, these different Hamiltonians for these two different theories. and what we noticed was that for the classical gravity one, there were now just 2 field operators coming from the stress energy tensor, and this means that it will necessarily preserve the Gaussianity of this matter field, which I'll explain a bit more on the next slide. So that means that Gaussian matter states can only stay a Gaussian matter state, whereas for quantum gravity, we now have another field operator, and this necessarily means that it can induce non-Gaussianity of this matter field, which, again, I'll explain a bit more in a second. So then the idea is that only in a quantum field gravity can a Gaussian matter state go into a non-Gaussian matter state. So if we were to see this in experiments, this would be evidence of quantum theory of gravity. Okay, so now to explain that in a bit more detail. So for those who are not so familiar with Gaussian and non-Gaussian states, these things are much studied in quantum field theory, where we have Fick's theorem. Also in cosmology, where you have Gaussian and non-Gaussian temperature fluctuations of the CMB. And they're also much studied in continuous variable quantum information theory. And one way to characterize them that's perhaps most used in quantum information theory is to split your quantum field into annihilation and creation operators, or expand it in annihilation and creation operators. And here I've just chosen a discrete mode spectrum for simplicity, and also a relativistic field. And then from these you can create position and momentum-like operators of a simple harmonic oscillator. Okay, and then a Gaussian state is one that's fully defined by the first and second order moments of these operators, just as a Gaussian function is fully defined by its first and second moments. But there are equivalent ways of defining Gaussian states, such as first and second order correlation functions of the field. And then it's been proven that a Hamiltonian that is just quadratic in these x and p operators will always preserve Gaussianity. So a Gaussian state will always remain Gaussian. And this seems to be the case, as we've seen for classical gravity, where now the gravitational field is absorbed into the coupling terms of the Hamiltonian. But yeah, there were equivalent ways of showing this as well, using, say, the path integral formalism of quantum field theory. Okay, so, but then in a more general setting, if we, say, couple this to another quantum operator, then you would find that now Gaussianity is not necessarily preserved, and this seems to be what we have with quantum gravity. Okay, so yeah, just in case there aren't any, just in case there are any that's not so familiar with these concepts, Gaussian states include vacuum states and coherent states, and squeeze vacuum states and thermal states. So in the bosonic case, these are characterized by a Gaussian Wigner function, which is what these are, and these must always be positive. Whereas non-Gaussian states include Fock states and cat states, and they have non-Gaussian Wigner functions, and in this case they can be negative. And interestingly, or at least to me, an entangled state can be Gaussian or non-Gaussian, and a separable state can be Gaussian or non-Gaussian. So in that regard, at least, there's not a strong correlation between these two different concepts. And whereas with entanglement you need 2 quantum systems, of course, you only need a single quantum system for it to be Gaussian or non-Gaussian. Yeah, so just quickly, the reason that non-Gaussianity is much studied in continuous variable quantum information is that it's needed for universal quantum computation over continuous variables. So that kind of illustrates the quantumness of these non-Gaussian states and operations. So if you're more familiar with discrete, universal quantum computation of discrete variables, then you can read stabilizer states for Gaussian states, and the magic states are the non-Gaussian states, the ones that are needed for universal quantum computation. Okay, so now that I've introduced this alternative approach, is there any benefit to using it over the traditional entanglement approach? Are there any advantages? So to help answer this question, I thought I'd first reiterate what I believe are the key main assumptions behind the idea. So these are that matter must obey quantum field theory in the experimental regimes of interest, and that this is accessible to the experiment. And also that, as with the entanglement argument, that we can neglect all the other interactions in the experiment. Okay, so then compared to this entanglement argument, noticeably we didn't include a locality assumption, which is why I spoke about that so much earlier. So yeah, there's no obvious LOCC here, so it's possible that non-Gaussianity does not rely on locality and could be used to rule out both local and non-local theories of classical gravity. So a further hint that this might be the case is provided by looking at non-local quantum field theory explicitly. So these are theories where you drop the locality assumption that is usually made a requirement of quantum field theory. And actually they're quite studied in the literature, particularly in the context of string theory. And they do often come with issues to do with things like causality, of course. But I'm just going to ignore those here just to illustrate the argument. So then if we want a non-local gravity and matter interaction in these type of theories, then we'd want to make sure that this doesn't occur at a single space-time point. So that's what you do in these non-local quantum field theories. You put in a Hamiltonian such as this, where in a normal local QFT, you would say x equal to x prime. Okay? But then, of course, this does not disturb the fact that classical gravity will preserve Gaussianity, because you still just have two quantum operators, which is all that's important in our case. So this theory will still preserve Gaussianity. In contrast, if you were to look at entanglement from this theory, now you can get entanglement between two space-like objects, which of course we already knew. We knew that we can get entanglement from non-local theories of classical gravity. So obviously I don't want to give the impression that I'm in favor of these non-local theories, just that non-Gaussianity may provide a way of avoiding this confusing discussion on locality. And it also happens to be somewhat connected to the fact that now we can just use, in principle, a single quantum system to detect non-Gaussianity, because you don't need two objects as you do in entanglement. Okay, so that's some advantages, but to be fair, then I should also talk about some potential disadvantages. So one at the moment is that there is no theory-independent approach, whereas this has been looked at to some extent for entanglement, as I've said. So it's lacking a more general approach. It's a bit specific, perhaps. The one very speculative idea we've had on that is to look at contextuality, since, of course, non-Gaussianity is connected to negative Wigner functions, as we've seen. And this has been shown to be connected almost one-to-one with contextuality. And then even more speculatively, perhaps this could explain why maybe locality is not an assumption, because in some regard you could think of contextuality as more general than Bell's theorem, because of course the latter essentially derives from contextuality over space-like regions. Okay, so that's all very speculative, so don't read too much into that. But one thing that we have shown that's somewhat connected to this. There's no paper on that. No. It's just it's more of an idea than anything. But but something that we have shown that's somewhat connected to that is that not in a paper though, just written up but not published, not in the archive, is that you would to properly get non-Gaussianity, you need non-commutativity of gravitational operators. And other things that we've looked at are specific cases, so non-Hermitian gravity, or where gravity acts as a weak objective measurements. Yeah, but as I say, a more general approach would be much better, which still needs some more work. And there could be other disadvantages, such as I don't think at the moment it's as intuitive, though a theory-independent approach might help. And it also needs matter to obey quantum field theory, it seems. Though again, a more general approach would help. All right, so let me leave the pure theory behind and go on to explain or introduce how you could use non-Gaussianity in a test of quantum gravity. It's okay, DEVANG, you've got 3 more slides and then it's your, then it's your turn. So this test is based on a single atomic BC. So that's where, of course, you have identical atoms macroscopically occupying the ground state. And yeah, these were first demonstrated in 1995. They've been now developed in many research centers around the world, including, of course, Vienna. And both gases are many-body systems. So a nice way to describe them is to use non-relativistic quantum field theory, where the quantum field psi dagger R would create an atom at position R. Okay, and then when the ground state is, in the approximation that the ground state is completely occupied, then we can approximate the system by just a single mode of the field, and then we have a single annihilation operator for the ground state. So then if you want to look at how gravity self-interacts, when you look at how the BEC self-interacts through gravity, it's reasonable to use the Newtonian approximation since the BEC is non-relativistic. And in that case, if we use a quantum theory of gravity, you find that the Hamiltonian is quartic in these operators, and so it will induce non-Gaussianity, whereas if you have classical gravity, it's quadratic, so it will preserve Gaussianity, which of course follows from the more general argument, but this is an explicit derivation for the BEC. And yeah, it turns out that naturally the BEC is somewhat in a Gaussian state to a good approximation. So if you see some sign of non-Gaussianity being developed in the BEC and you can attribute this to gravity, then this would be evidence of a quantum theory of gravity. Okay, and then you can develop a signal-to-noise ratio for this measurement of non-Gaussianity in a BEC due to quantum gravity. And for a spherical squeeze BEC, it just so happens that this takes a very similar expression to the phase that we saw in the entanglement experiments, which characterize the feasibility of those experiments. We just replaced the distance between the microspheres, in that case with the radius of the BEC, and we introduced this curly M, which is the number of repetitions of the experiment. So then if you want a similar signal to the entanglement experiments, you need at least 10 to 9 atoms in your BEC, which is very large for BECs. It has been achieved to some extent in the past, but as DEVANG will explain, much more work is still needed there. On top of that, of course, you need to squeeze the BEC and maintain it for a second or so, but at least squeeze states of BECs have already been produced in the lab. Okay, so before I pass you on to DEVANG, let me just summarize from a more theory point of view. So this is a test based on a single quantum system. In principle, is not reliant on local interactions. You don't need these challenging spatial superposition states, often called noon states. Hopefully, it would have good repeatability, as with other BEC tests. And there is already some quantum technology for the initial states and measurements needed. But at the same time, I don't want to oversell the proposal. Of course, it's very challenging. I couldn't do it tomorrow. But now we're working on ways to try and bring this closer to experimental reality. So that's the goal next. Okay, let me now pass you on to DEVANG finally. You can provide a lot more detail on the experiment.
You pose now the questions already?
Oh, I don't mind. Yeah.
Is there actually an idea of how you maybe can optimize this? What you formally have are 2 Hamiltonians that you want to distinguish. And there is a lot of things that have been done in quantum information on black box distinguishability between 2 unitaries. You have one or the other unitary.
Yeah.
Then you can optimize the initial state, and then you can optimize the final measurements to distinguish between them.
Yeah.
And it could be that the state that you should start with is maybe not Gaussian at all, and maybe the measurements are not measurements of Gaussianity, but something more.
Yes, I completely agree. Yeah, I think, I mean, that's Yeah, thanks for that, because that's an avenue I should explore, actually. I hadn't thought about these black boxes, but that's certainly something that we're looking at now is, what could you take a different initial state, like a non-Gaussian state, which may be better? Or can you even go to almost like a classical state, which then would be a Gaussian state, like a coherent state, and then we get rid of these experimental challenges, and we have some ideas on this. Rather confusingly, it would be one of them would be to not look at non-Gaussianity anymore, but to look at squeezing, because this non-Gaussianity, we try to make it as general as possible. So it applies in like the relativistic regime of quantum gravity as well as non-relativistic. But of course, these experiments are going to be non-relativistic. And in that case, this Gaussianity signal actually becomes a squeezing signal. So that is like another way of trying to make the initial states better. But yeah, I should definitely look at thinking about this in terms of black boxes and unitaries. Yeah. Thanks.
I have another question.
Yeah.
Perhaps it's silly, but so the wave function of the field that describes the Bose-Einstein condensate is like an emergent degree of freedom, right? It's like the order parameter. How general is the coupling that you assume, the gravitational coupling you describe in terms of which side? Like, it's not the same as the amount. It's not the same as the cumulative effect of each Newtonian interaction, or is it? You mean because the wave function is I'm not thinking about each individual atom? Is that what you mean? I guess the question more generally posed would be, how do you postulate the gravitational interaction for this field psi?
How do I think of the gravitational interaction? Yeah.
Like I see it as formally it's a simple way to write it, but is there more to it behind it? Or?
Oh, well, I mean, okay, so, well, let me see if I answer your question when I speak about it. So this interaction derives from, like you could derive from weak field gravity, right? This is the field describing the atoms. The whole Bose gas, of course, and then you take the approximation that the ground state is the one that dominates. Do you mean like if we didn't use a quantum field to describe the atoms, or you mean like?
That is exactly the integral of two particle interactions.
That's right. That's what it is. Yep. Yeah. That's exactly what it is. Yep. Okay, maybe you want to go on? Oh, we need to do this, don't we?
I could just start off. I just want to thank everyone for coming here, and thank you, Marius, for organizing all of this. I'm a complete experimentalist. However, when I started my studies at Georgia Tech, there was David Finkelstein, the Finkelstein-Eddington coordinates, and I was his teaching assistant for a while. And he would always talk about a lot of these things, quantum gravity, and I was lost. I was trying desperately not to say anything dumb. And the last 2 days here, I felt the exact same, listening to Kaslov and Marius and Richard. So, okay.
We feel the same, don't worry.
Does anyone know the password for the laptop?
Does it say on the laptop?
Oh, does it? Okay. Yeah, you're right, it does.
Because it wasn't open?
It's saying it's unsupported to files now.
But we okay.
What's a new password? Okay. So, change the password of the laptop. I had to change the password of the laptop, so I better remember what I changed it to. Oh, nothing. I just need to. That's now a 6. For some reason, it expired. So I might have to use it. Sorry, I hadn't worked.
No. Just sleep.
Press this.
Yeah. Okay, the first one.
First one. That's it.
Perfect. Ah. Okay, perfect. Okay. Ah, perfect. Okay. Okay. Thank you so much.
Thank you, Richard, for
Yeah. I'll just use that and I'll use this.
It's okay? Yeah.
Okay. So actually, I just want to convince you that ultracold atoms can maybe also serve as an experimental platform for a lot of the theories that you're working on. Of course, here you guys have really amazing experiments using the microspheres and microscopic objects. And they're definitely much more advanced than we are. However, there are certain advantages we could give you. To give you an idea of the technology that we have, I always find is interesting. So this is sort of the temperature scales that we have. Now, this point is the freezing water and boiling water. It's a small point here. And this is the surface of the sun. So most of our everyday experiences are in this small part of the graph. But now, with the technology we have in the recent decades, we could go all the way 9 orders of magnitude to temperatures over here. So just being able to span this entire temperature range is one of the great sort of advances in ultracold atom physics. And this is done via optical cooling, which of course won the Nobel Prize, and evaporative cooling. And the combination of these two things allows us to get to nano-Kelvin temperatures. But the requirements of these two things kind of limit us in terms of the atoms we could use. So far, these are the atoms that we could cool and trap to quantum degeneracy. It's actually a wide range in some sense. And depending on the properties, tells us what we could use them for. Now, I really just want to talk about the atoms we could use for these types of measurements that we're talking about here. Most of the times when I talk to theorists, and they're talking about using ultracold atoms for these sort of effects, they talk about really crazy numbers, 10 to the 10, 10 to 11. In fact, lots of times the first line of a theoretical paper is, assume we have 10 to 11 atoms in a BEC. And I keep wondering, where did they get these numbers? Because lots of times we work with 10 to the 3, 10 to the 4. And they get the numbers because they talk to one particular group, the group of David Doyle at MIT, who works with hydrogen. Now, hydrogen, they have been able to create huge atom number BECs. I think now, the last published one was like 10 to the 10, but I think now they say it's close to 10 to the 11. And this is impressive. However, it's hydrogen, so it's not as massive as other atoms. The reason it's so good is because it has close to 0 three-body collisions. And you could really use collisional evaporation to go to really, really low temperatures. And also, they don't form molecules. But there's one big issue with hydrogen, and that is the BEC fraction. So even though you have huge amounts of atoms in the BEC, you have even more atoms that are in the thermal state around the BEC. So you're always going to have collisions between these. So creating an isolated system is a bit more difficult. And also, they don't have really good optical transitions. In fact, they're in the extreme UV, and lasers just don't exist. Yeah.
So, what fraction of the atoms is in the BEC state?
About 5% for them, for hydrogen. And if you ask them technologically, they could go to 10 to 11, 10 to the 12, but the BEC fraction will still remain the same. So yeah. And this extreme UV lasers in this region, in the 160, 170 nanometers, are really difficult to come about. I want to include this because you guys have a really impressive experiment with helium. Helium is a noble gas. However, you could put helium in a metastable state and use it just like an alkali atom and create BECs and whatnot. The interesting thing about helium is the experiments can arrive at single atom detection efficiency, which means a lot of the quantum optics experiment that Anton Zeilinger did with the photons, you could do with helium. And in fact, the lab here actually does this. However, this is also light, and you need metastable states. There's small BCs and low mass. Now, this, yes? Anton Zeilinger? He has a helium experiment here. Yeah. It was first done in Paris by Christopher Westbrook. And Christopher Westbrook showed these really nice experiments where you could create momentum-correlated states. And you could do Bell's inequality experiments with that. And then they built an upgrade of the experiment here. Because in France, they're getting rid of all these helium experiments. They're very complicated, very expensive. And we don't have that much money in general for research in France. Now, this is, I kind of started with this atom, sodium. It's kind of the, I love that atom. I'll show you some photos, but one of the nice things about this atom is it glows in a yellow color. So when you enter a sodium lab, you see all these beautiful colors. This was one of the first BECs that was created, and one of them won the Nobel Prize. Now, the advantage of this is ratio of 2 to 3 body collisions is perfect for ideal. The only one better is hydrogen. The hyperfine structure was almost created for laser trapping and cooling. And the second largest BECs have been created with this. It was first our group that did this. We had about 100 million atoms. And then the group in the Netherlands beat us. Now they have 500 million atoms. And we think we can improve slightly on this. These are sort of the experiments. This was my experiment. We have these beautiful lasers. We use dye lasers. So you see beautiful colors. You have green lasers, yellow, and blue. This is a particular experiment we created with about 300 million atoms. And the entropy of a particle is really low, which means the condensate fraction was extremely, extremely low. The thermal cloud was very small above it. So you really talk about doing experiments with cold atoms. This is a picture of a moth. It really looks like the sun just flares up. And then what we can do with these large atom numbers, we could actually rotate the superfluid and create these vortex lattice states. So we take the BC and spin it really fast, and we create a vortex. However, in the quantum regime, the vortex wants to minimize its energy. So instead of the atoms wanting to spin around with large angular momentum, the vorticity breaks up, and we create small vortexes. Each of them has 1 unit angular momentum. And you could think of this as an atom simultaneously orbiting every single one of these at the same time. At the same time, we could actually create these steering wheel type condensates. This is a trap with the 300 million atom condensate that exists in like a thin ring steering wheel. This is an image when you expand it in time of flight. So these are one of the things that we were really interested in at that time, although we stopped this experiment, was creating superpositions of angular momentum in one direction or the other. We stopped it because, well, there was no really theoretical interest at that time for it. But if there ever becomes one, this would be an interesting thing to start back up again. Now, if we're trying to create large BCs for the type of experience we're talking about here, sodium would be the best candidate. What we need is we need large initial phase-space densities before we begin evaporation. Because evaporation, we just have this really dense thing. We start kicking out hotter atoms, and we let the rest of the atoms thermalize to colder temperatures. This is nature's most efficient cooling method. However, it's very sensitive to initial conditions. So the more we can start, the better conditions we have at the beginning, the better it can be. So just going from 100 million to 500 million, the other group that beat us, they increased the initial phase-space densities just by 10%. But that 10% made a huge difference. You need good 2 to 3 body collisions, which sodium already has, yes? In principle, you cool things down to hundreds of microkelvin. Then you put into a huge magnetic trap. And this is going to be the trap where you do all your experiments. However, it's too hot. It doesn't create a BEC. So we want to cool via evaporation. So we take hot atoms, we kick them out. The rest of them will re-equilibrate. The beginning of this evaporation process, we want enough collisions, enough densities, and cold enough to where this process of kicking out an atom and cooling the rest of the atoms increases the density to where we could kick another out and increase the density more. It gets into this runaway regime. And this is a nonlinear process which is very sensitive to those initial conditions. So if we increase that initial condition, we gain a lot. Also, we take lots of time. So we required 60 seconds to create one BEC using these methods. The group that beat us requires 100 seconds. So they could almost start the experiment, get a coffee, then come back, and they get one piece of result in that time scale. In order to get these times, we need a lot of really good vacuums, and we need all other forms of heating to be minimized. The biggest form of heating that everyone has is the magnetic fields. The current they use to create the magnetic traps has noise on it. And this noise actually slightly heats the atoms while we're trying to cool at this level. So we have to design new types of current supplies, which we kind of done, which I could talk a little bit about that, but it's very technical. So these are things we need. Now, recently, we made an advancement. This is actually in a project with Professor Risch, which is sitting back there. We had a new type of cooling method, pre-cooling method, using dark states. Now, the advantage of this is this allows us to cool from millikelvin to about tens of microkelvin in less than 100 microseconds. It's really fast, which allows us to really get the good initial conditions. In fact, we're able to improve phase space density by a factor of 7 with respect to the original methods. This is sort of the initial phase space densities. This is what most other labs use. This was our previous method, and we have some improvement. So we have a little bit of hope in getting to the conditions that Richard talked about. We actually use this. Instead of creating large BCs, we created small BCs, but very fast. So one of the things we want to do is create portable quantum sensors. This is our BEC machine. It's about 1 meter by 1 meter by 1 meter. Using this method, the high phase space density, we're able to create evaporation ramps to where we could create a BEC really every 1.5 seconds. And then we could do this repeatedly, 24 hours a day, 7 days a week. We have this thing that we built. This is an elevator, which just goes up and down. This can create accelerations. We could create for 400 milliseconds either 0G, 10G, or 100G. We want to see kind of how phonons or how these sort of quantum systems can behave in different gravitational fields. One of the things is test of weak equivalence principle. And recently, this is a little company in Bordeaux, France. They do 0G. It's a plane that just does these things. Recently, we become flight qualified, so we could take this experiment and go on here. And this gives us about 10 to 15 seconds of 0G, and then 2G, and then 10 to 50 seconds of 0G. So now this experiment kind of routinely goes on here. The funny thing was this was flight qualified. We're waiting for space qualification. However, in doing all the flight qualifications, we forgot that the people also had to be flight qualified. So we were not flight qualified. So we had to put this on the plane, but we couldn't be there. And this point's another advantage, which I'll mention. All of our experiments now are controllable online. So they run 24 hours a day, 7 days a week. We have a program that if there's a Wi-Fi connection, we control it online. There's even a group in Bonn who actually has created an app. And they can control it, their experiments on their cell phones, which is we have not arrived at that level. But OK, this is sort of creating big BECs. But one of the advantages of ultra-cold atoms is we could tune it. And one of the biggest tuning knobs for me is Feshbok resonances. So after this is an experiment we did actually in Innsbruck, in the Koki, but in Innsbruck. We had a built experiment for lithium, potassium, and strontium. These have both bosonic and fermionic isotopes, but they have Feshbok tuning. I don't know how familiar everyone is with this. For me, this is one of the coolest things. So you could actually control two-body interactions just using magnetic fields. So at the temperatures we're at, the atoms can only collide via S-wave collisions. This is sort of the collisional wave function. It's sort of van der Waals. When they're far away, there's zero collision energy. When they come together, there's attraction where they can form molecules, and then repulsion. And this is just this scattering length, which is here. It's just given by nature. And more importantly, it's given by this thing E sub B, which is the last bound molecular state here. If you know this, then you know the scattering properties. Now, these are alkali atoms. So each atom has one electron here and one electron here. These electrons can form a singlet state, in which case they have one scattering potential. Or they could form a triplet state, in which case they have another scattering potential. And this one has an energy difference, which you could tune with a magnetic field. If you go to a magnetic field, where a bound state of this triplet is exactly on resonance with a value in the singlet state, you arrive at a point where the scattering length is given by a quantum superposition of these two channels. And this allows you to tune the scattering length. You could go from 0 to plus or minus 10,000, A0, to 0 again. So this is about 4 orders of magnitude in terms of tuning. Now, to give you an idea, the natural scattering lengths are about 100 A0. So it allows you to go really a large distance. And it allows us to access the universal regime. These are interesting things where the scattering length is so strong that everything else drops out of the equation. So any trap inhomogeneities, imperfections, you don't have to worry about because the scattering length controls everything. This is a type of experiment that we create. You see that they're huge. They take the size of this entire room. You have this oven, which creates lithium, potassium, strontium. They're cooled in a Zeeman slower. They go to this glass chamber, this over here, where we could cool them. Here's an image of lithium and strontium. There's also potassium here, but you can't see it with your naked eye, but it's there. And we could do spectroscopy. The only reason I'm mentioning this is in order to do this, every single point takes about 5 minutes, and we had to take many, many points. This experiment was running 24 hours a day, 7 days a week for six months to do the spectroscopy. But this just shows you that with ultracold atoms, we're at a point where statistics is not an issue anymore. As long as you have money, it's not an issue. And these are kind of interesting things we're able to do here. We could take free atoms, free lithium, potassium. We could coherently create molecules out of them and then dissociate them. These are Feshbok molecules itself. You can see the signature here. Lithium is light, so it expands really fast. Potassium is heavy, so it doesn't expand. However, when they're molecules, lithium expands the same as potassium because it's tied to a molecule. This can be used to create momentum entangled, mass entangled by momentum entangled states, by the way. The other thing which is nice is we have full control of the optical potentials. So using optical lattices, we could confine them in lattices and also in one-dimensional tubes. In fact, here's the experiment where we have rubidium and potassium. We have a Feshbok resonance, so we can control the interactions. And we have them in one-dimensional tubes. In these tubes, we could reduce 3-body losses by 5 orders of magnitude. So with the ultracold atoms, we have full control over 2 and 3-body losses. This is a case where we could take these potassium atoms and we could create polarons. And these polarons, we could study their dynamics. So these are collective kind of sort of modes. This is another experiment which is close to my heart. We have potassium, really cold, so it's a matter wave, inside a tube. We have rubidium, and we have strong interactions, so we create a collisional barrier. And we can see tunneling of the matter wave inside this one-dimensional tubes. Now, this is a controllable parameter. In fact, the spatial extent of this collisional barrier is huge. So in principle, we could do measurements inside of here. And one question I always have is, can we actually measure particles while they're tunneling? This is also a fundamental. This is basically Heisenberg uncertainty principle. So in principle, can you do experiments like where you could really probe Heisenberg uncertainty principle in these tunneling experiments? But now, I've talked about creating quantum states. The proposal we talked about was actually how to measure it in a really nice way. One of the ways that we mentioned in the paper to measure these quantum states is higher order correlations. So 2-body, 3-body, and 4-body correlations. So how do we do that? This is one advantage also of ultracold atoms. We have really good measurement techniques. One thing we could do is when we have these ultracold atoms, we could take images of them. These are atoms inside a 3-dimensional lattice. And we take an image. This is just the density of the atoms. And you can see we can't see any effect of a lattice. However, if we take a slice of this data, we see noise. Inside the noise, we have really important information. We could calculate noise-noise correlations. And we could do this because we have this BEC here. We take an image. This is our camera. The camera is composed of pixels, and we could treat each pixel as an independent detector. So now we can do correlations between different pixels, and we have 1,000 by 1,000 different sort of combinations that we could use. This is sort of one of the things that you see. Here we create an experiment where we had a lattice, and we put an atom inside every lattice site. However, we couldn't image this lattice because we didn't have the resolution. But doing noise-noise correlations, we get an image like this. What this is showing here is this is showing that the distance between these peaks tells us the actual spacing of the atoms inside here. If I change this lattice, and I create a lattice with every other site occupied, I can see new peaks occurring here. This actually tells us information about what's inside the lattice. Our idea is to actually take these concepts and move it up into the fourth order that we need for this sort of experiment. We also can do single atom detection. Using cavities, we could measure the possibility of having a single atom inside here. Now, another thing that we have is we have full control, as I said, full control of the spatial properties. This is also another experiment using cavities. This is a particular experiment over here. There's a cavity shaped in a butterfly like this. Now, the type of optical modes that can exist in a cavity are written here, the TEM modes. We could have a cavity with this mode, which we inject. It rotates around this cavity, and it crosses in the center. And here we could put atoms. These are atoms in this mode. We could also use this mode, and we could create 4 trapping geometries right here. This is just 2 nodes that are traveling around the cavity. They intersect in the center and create 4 nodes. Now, why do I mention this? Well, because we could do something here. We could use a combination of these to create a beam splitter for the BECs. These are kind of one of the building blocks that we need to do quantum optics experiments. We could take a BEC inside this node and split it into 4 BECs, which is what I show here. This is an image of a BEC. We split it into 4 coherently, and then we recombine it. Now, how do we know it's coherent? Well, one of the things we could do here is we could imprint phases onto here. Suppose we send lasers and put a phase difference between here, which is pi over 2, another pi over 2, another pi over 2, another pi over 2. Now we have 2 pi phase difference inside here. A 2 pi phase difference, when we recombine them, that 2 pi phase difference interferes and creates vortices, which is what you see here. So one of the things that we could do with this is phase engineering. We could if you tell me what you want, a new novel system, and you could show me the phase, we could imprint the phase on here and create the system. So it allows a lot of control in this sort of way. This is also another thing we could do here. We could create linear box-like trapping potentials inside of a trap. This is a BEC inside of a box-like potential, and it's expanding. And you can see it has a shape. So it gives you a lot of possibilities. Okay, I would kind of like to conclude in this case. I would like to say that there are certain advantages of using ultracold atoms. They're accessible, they're tunable, they're isolated. We can go into the ground state of all our variables and create quantum superpositions, and we can create deterministic, repeatable protocols. All right, thank you for your attention. The
correlation mass.
yeah. Okay. So take the atoms in a lattice here, and then we expand them. So now they're falling, and you have a camera here, and then we take an image. Now you have an atom here which could fall to this pixel. You have an atom here which could fall to this pixel. But at the same time, this atom can go here and this atom can go here. Because they're bosons, these paths can constructively interfere. And that's exactly what we're seeing here. Every one of these points is a point where there's a constructive interference from a boson here and a boson here. Now, in this particular case, there's not a boson here. So the constructive interference can only come between these 2 bosons. They're further separated apart. So we get extra peaks. Now, why do we get extra peaks? In principle, you would think if they're separated further apart, we should see less peaks. One of the things in here is we don't actually measure in the space of these atoms. We measure in the momentum of these atoms. So it's in the Fourier space. So that's why you get it twice, yeah. But in principle, any experience where you need momentum correlations, like what they do downstairs, you could in principle do in these systems too. And actually, we're looking for sort of more ideas on this. We have a technique, but we don't have ideas on what to do with it.
Is it published?
Yeah, I can send you the, yeah. There are many different methods of doing this. This is just one particular method. The advantage that we have is we have good spatial resolution in this direction, but not in the z direction. Whereas what they have downstairs, they have great spatial resolution in the z direction, but not in the xy. So, yeah.
Other questions?
Very nice question. If you have the gravitational interaction in a lattice, and you have sort of a two pair occupied spot insulator, would you get a strong effect or weak effect, or would you get?
So we do, like, so you mean a multi-insulator vertically oriented, right?
Or just could be a maybe three-dimensional multi-insulator.
Yeah.
No, you just
So we were.
you have these pairs very tightly.
Yeah. Well, we were talking about a configuration. So take a multi-insulator like this, and then create a superposition between this, every other occupied, or this one, boom.
Yeah.
This. Yeah. Actually, that's the question I posed. And maybe I should look at Marius for this.
Don't know.
So in terms of creating, so a lot of people talk about creating huge BCs and put them in superposition. This would be much easier to create. It's the same mass in superposition, but we don't have to go that far. However, there's no spatial overlap between the masses. In my opinion, it should be, but yeah, that's a question. That's why I'm here, actually. So I don't know if Richard and Marius, you have more.
It's too speculative right now. We just have many pictures, but we haven't seen any equations. So we if there is a protocol to see gravity-mediated entanglement using, instead of trying to have two masses that are large enough, so that you can see the effect, having smaller masses trapped in.
Where you have many times
Yeah.
pairs, so with many pairs could be really many pairs.
Exactly. So you will need to have many smaller masses, but then you will have them all becoming a tandem. You will need that pairwise entanglement. We need to create some sort of null state, and that's what we don't understand.
Yeah, with pairs you have a certain chance of a new state. Otherwise it's a bit difficult. But hey, I didn't think about it, so
Yeah.
I don't know if you know the work of Marcus Greiner, but he created basically this whole lattice of this in one dimension. And he created a superposition of the entire lattice with something one spaced away. He claims that the entire lattice is one entangled state. I don't know if that's a true claim or not, but I don't know if you know this work.
yeah, I don't know his name, and in the proof, if you go back, you have to end up with zero entropy again.
Okay.
And that's the only way to prove it, but then you don't want any evaporation or any cooling, anything
Yeah,
going on, which is, I think, at the moment impossible. But
yeah, that's true.
I mean, it's not, it's cold enough at the end. I don't know. It's not a proof, but it's maybe a hint, a good hint.
Okay, it's good.
What is that? To show that it's reversible. Why do you want to go back to zero?
Well, then you basically have done something quantum. When if there is a classical step in between, then there will be some excitations left at the end.
So the way to show that there was entanglement is to show that there was zero.
I mean, you have to be all the time in a pure state.
Zero.
Okay.
Zero thermodynamic energy.
Yeah.
Yeah.
Okay.
Not entanglement actually. That's why.
You know, if you make partial traces, you get entanglement, of course.
Okay.
Different entropy, that's a different way.
Okay.
So on what metric is the non-Gaussianity experiment?
In this case,
What are the hardest numbers to achieve?
yeah, actually the numbers I think we could achieve. The squeezing. Because the squeezing, so we've been able to do squeezing, spin squeezing. In this case, we would need position momentum squeezing. Now, there are sort of, wait. Do I have this? Okay. We have another experiment on biological systems, by the way, using quantum sensors for neural imaging. That's what all this is for. If anyone's interested, please let me know. Okay. So here's a case of a big cavity, huge. The line width is smaller than the recoil. Now, if you look at the atom cavity interactions, you could actually you take a BEC, you turn on the interactions, and the cavity kind of kicks. There's 2 photon transitions, and you get a kick, boom, boom. And that's what all these are. So now you have something that's sensitive to momentum. The question is, can we use this to create some sort of momentum squeezing or momentum entanglement?
What do you need the momentum entanglement?
Well, we want is squeezing in the momentum space, right?
Yeah, squeezing in the momentum case just means that it's like quantum metrology, right? Like, so you reduce your noise in this measurement, so that your X measurement is good, or either of that. So
Okay, in this case, which one do you need? You need
it doesn't
the
matter which
momentum.
way you go, but maybe it's easier to do momentum squeezing. Or, I mean, but saying that, I mean, we are looking at ways of getting us you don't have to do squeezing, but that's still progress.
And the squeezing, because if it's not squeezed, it doesn't become a non-Gaussian, or is it the squeezing?
No,
makes it
no,
faster?
squeezing is nothing to do with, yeah, it doesn't matter if it's Helium, it doesn't go non-Gaussian, but squeezing is a way of improving the measurement scheme, basically.
Is the signal to noise ratio?
It's, yeah, yeah.
Okay.
It's your noise reduces. Yeah.
Okay.
Yeah. Now, you can always do something in, sorry, yours.
No, I understand.
Okay. You can always do something in spin state and then with the magnetic field evolve it into momentum. But then anything that could decohere the spin will now decohere your real variables. But yeah, this will be, I think this will be the hardest. Yeah.
Yeah, no, I get it.
But still, we're thinking 10 years down the line.
So the number of atoms is achieved already?
Well, no, okay. Well, the mass, the numbers, of course, but the mass, because we're talking about cesium atoms in the paper, 10 to the 9, 10 to the 10 cesium, 10 to the 9. Now, we've achieved 10 to the 8 with sodium. I think we could achieve mid 10 to the 9s with sodium with our new method. That kind of gets us in the ballpark, although sodium is lighter than cesium. So that will kind of get us roughly in the ballpark. One of the things with these big things is when you use light, even more interesting things occur. So if you send a single photon inside this boson, one atom could absorb it, but then you have bosonic stimulation in many different directions, so it could cause lots of matter waves and everything from forming. So you want to do all these things without breaking up the BEC into interesting condensed matter systems. So this is also another thing. So basically, creating that BEC is just one thing, but manipulating it, these large BECs, is a very difficult matter. And that would probably be the biggest sort of challenge. Yeah. And just so you know, we don't need cold temperatures. This is a experiment where we use room temperature in tangle states to measure a neuron firing of a frog sciatic nerve. So in principle, we don't need cold temperatures to do any of these physics that we're talking about. Even room temperatures, we could do interesting things. So yeah, I'll leave it at that.
Is there any other questions? Okay.
Okay.
First speaker.
Actually, there are neat things we can talk about. So for us, you and I learned something.
Oh yeah, yeah, maybe I did, yeah. And you also, yeah, that's
Yeah.
good stuff in that. Yeah, I enjoyed
Results.
it. Yeah, no, it's very good, very nice.
I'll be up in the top floor.
Top floor.
There is in the highest floor towards there.
Okay. What time?
Whenever you have time, you come up.
Okay. We could come up now. Actually, I could come up now. That's okay.
Yeah.
Oh, okay.
Fine.
I'll just be back.
Yeah, of course, do you want to?
What to do?